This lecture is going to be about plotting and color in R. It's kind of an adjunct lecture to the lectures that we've already had about plotting in both the base graphics and the lattice graphics system. I just want to talk a little bit about how you can specify different types of colors using different palettes in R. You might think that the specification of color in a plot is maybe kind of a secondary decision, and in some sense it is. It's definitely secondary to something like the data. But of course, the judicious and appropriate use of colors, I think, in plots can help to describe the relationships that you're trying to demonstrate, and can help various dimensions of the data come out more effectively than if you just choose an arbitrary set of colors. So there are a couple of functions and things I'm going to cover in this lecture, but the basic point that is that the default color schemes for most of the plots in R are pretty bad, and you don't have to be an expert in design or anything to really kind of see this. But the kind of the natural color schemes that you kind of gravitate towards when you use the plotting functions are not particularly well suited for different kinds of data. But there have been a number of developments in R via packages and also in the core R system that can help with the handling and specification of colors in various types of plots. And so I'm going to talk about one of these packages and some of the functions in this lecture. So the basic problem that typically comes out in most plots is this is a pretty standard plot in R that you might see in a presentation or in a paper. There's some points on the plot, and I'm just plotting random points here. And you see that the points are in three different colors. The first is black. The open circles are in black. Then there's a couple of points that are in red, and then there are a couple of points that are in green. So why does this happen? Well, because when in most plotting functions there'll be a call argument, col, and when you say call equals 1, you get black. When you say call equals 2, you get red. And when you say call equals 3, you get green. And so if you have a plot and you want three different colors in it, it's very easy to say, okay, well, just give me call equals 1, 2, 3. Um, and so you get black, red, and green. Call equals 4 would have been something like cyan, and then call equals 5 is magenta. So those are the kind of standard colors that you just get stuck with when you set call equal to be 1, 2, 3, 4, or 5. And so if you go this route, the red and the green are not particularly meaningful in this case. Of course, you don't know what the data are about, so it's possible that they are. But in most cases, they're not the most suitable colors for the type of data that you're going to show. And also, just from a design point, if you use this color scheme all the time, then all of your plots will look like they belong in some Christmas show or Christmas presentation. So the question is whether or not we can choose a better set of colors that better communicates the ideas that we're trying to get across. Another standard set of colors is shown here. This is the volcano data set that comes with R, and it's basically a data set that shows different elevations of a volcano. And the set of colors on the left comes from the heat colors palette, and so this is a palette of colors that goes from kind of a reddish to indicate low to a yellow or white to indicate high. And then on the right side here, we've got a palette of colors called the topo colors or topographical colors. This goes from a kind of blue, which indicates low, to a brown or a white, which indicates high. So for the heat colors, if you kind of know what fire is, it may be reasonable to kind of see that picture and know that kind of what is kind of low and what is high. For the topographical colors, it's maybe not immediately clear to some people what is low and what is high. It's not so. The fact that blue is low and green is higher than blue, it may not be particularly obvious. It's not particularly obvious to me. So the GR devices package has a few different functions to help you deal with colors, and the ones that I'm going to talk about in this lecture are the color ramp function and the color ramp palette function. Basically, these two functions take palettes of colors and interpolate between them. So the model that you can think of is basically, if a painter has his palette, and there are 4 or 2 or 3 blotches of specific colors on that palette. And then what you might do is take your brush and kind of mix between the various colors of the various blotches on that palette to make new colors that are blends of the original colors that you had on the palette. So I've never done any actual painting, so the only thing I know about painting is from TV and movies, but that's kind of what I imagine a painter would do is take these primary colors and then blend them together with the brush. And so that's what the color ramp and the color ramp palette functions do. They take a set of colors that make up a palette and they interpolate in between them, numerically of course, to make new colors that are blends of the original colors. Another function that may be of interest to you is the colors function, which you just execute it with no arguments, and it gives you a character vector of all the names of the colors that you can use in a plotting function. So these are colors that you can reference by name rather than having to reference their kind of red, green, and blue values that we'll talk about later. So the color ramp function specifically takes a palette of colors and it returns another function. And this function that's returned by color ramp will take values between 0 and 1, indicating the extremes of the color palette. And so a similar function that already exists in R is the gray function. And the gray function interpolates between black and white. And so it gives you kind of all the shades of gray that are in between black and white. The color ramp function is a generalization because it'll take any set of colors in your palette and it'll give you a function back that takes numbers between 0 and 1 and can interpolate between the extremes of the color palette. The color ramp palette is a very similar type of function. It takes a palette of colors, and what it does is it returns another function that rather than taking a value between 0 and 1, it takes an integer argument and will return a vector of colors interpolating that palette. So this is similar to the heat.colors function or the topo.colors function. So let's just, a very quick example here. In the top here, I've created, I'm going to use a palette that consists of two colors, red and blue. So you can imagine that on your little painter's palette here, you've got a blotch of red and a blotch of blue. And you're going to mix them together in varying degrees to create new colors. So when I pass this to color ramp, it returns a function back. And that function I've called pal. And now pal can take numbers between 0 and 1. So when I say pal of 0, what do I get back? I get a little matrix here with 1 row and 3 columns. And the 3 columns indicate represent the colors red, blue, and green. And so in the first column, I've got 255, which is the maximum value that I can have in this for these colors. The numbers that you can specify go between 0 and 255. So there's 256 total numbers that you can specify for each color. And so when pal is when pal is 0, gives the argument 0, basically what it gives me back is red, because that's kind of one end of the color spectrum that I've specified in my palette. The other end being blue, of course. And so I've got the maximum value for red, I've got 0 for green, and I've got 0 for blue. So that color is red. When I say pal of 1 down here, you see I've got 0 for red, 0 for green, and then I've got the maximum 255 for blue. So this just gives me the color blue. So that's the other end of my color palette. So what if I do something in between, like pal of 0.5? So this gives me something this should give me a color that's kind of in the middle of red and blue. So it's going to give me 127.5 for red, and then 0 for green, and 127.5 for blue. So it's kind of half red, half blue, whatever that color is happens to be. Notice that there's no green in any of these calls because when you interpolate between red and blue, you don't encounter green along the way. So if I were to give a sequence of numbers between 0 and 1, PAL would give me a sequence of colors between red and blue. So here I'm giving a sequence between 0 and 1 that's a length 10. So it starts at 0 and it ends at 1, and there's 8 numbers in between. And so when I pass this sequence to PAL, you'll see at the very top here I start with red, so it's maximum red, and then 0 for green, 0 for blue. And I slowly reduce the red amount and increase the blue amount until I get to the bottom here where I've got all blue and no green and no red. So those are the various colors that you get in between red and blue as you interpolate the palette. So that's the color ramp function. The color ramp palette function is very similar, but the type of function that it returns is slightly different. So here I'm passing it a different palette. So this palette has 2 blotches. It has a red and a yellow blotch on it, and we're going to try to interpolate between those 2 colors. And so I've got a function here that's returned by color ramp palette called PAL. And now PAL is going to take integer arguments, not numbers between 0 and 1. So suppose I give it 2. So pal of 2 will return 2 colors that interpolate the palette. Now, because the palette itself only has 2 colors, it won't act, when I just give it 2, it'll just give me the 2 colors on the palette, so the first being red and the second being yellow. And so the way that the format here is slightly different. Instead of giving a matrix with red, green, and blue values, it gives me a character vector which has numbers for or values for red, green, and blue that are represented in hexadecimal. And so if you ignore the pound symbol there, you see there are 2 digits, there are 6 digits in each character string. The first 2 represent red, the second 2 represent green, and the third 2 represent blue. So you can see for the first number here, I've got FF0000. So in hexadecimal, F is the largest number you can have. So FF on the red pair means a maximum for red, and 00 for green, 00 for blue. So that's red. In the second string here, I've got FF for red, FF for green, and then 00 for blue. So I've got the maximum on red and the maximum on green, and I got nothing for blue. So what does that give me? Well, that gives me yellow. I mean, I combine red and green, I get yellow. And so that's the other end of the spectrum on the palette. So now if I say pal of 10, you'll see the first element here is going to be red because it's FF on red and 0 on everything else. The last element here is going to be yellow because it's FF on red, FF on green, 0 on the blue. But then in between, I've got my interpolation of colors. So you'll see that there'll be some red, and then there'll be mixing a little bit of green as you go along here. For all the colors, there's no blue because you don't encounter blue when you interpolate between red and yellow. So you can see now the representations of the colors in hexadecimal here changing as you go from red to yellow. So you might be wondering, well, where do I come up with interesting palettes of colors? Well, you can always create your own palette of colors, just as I did in the previous slides, by indicating colors like red, yellow, or anything in the colors vector that you get when you call the colors function. But you might want to come up with some more interesting color palettes, and that can be done using the R Color Brewer package in R. So the R Color Brewer package is available on CRAN, and all it does is it provides a set of interesting palettes that you can use for different types of data. And this package was created from work that was done by Cynthia Brewer, who's at Penn State, and she's done a lot of work researching appropriate colors for creating maps and for mapping data. But these palettes can be quite useful for other types of data that don't really occur on maps. So the 3 types of palettes that you can get from the R Color Brewer package are the sequential palettes, the diverging palettes, and the qualitative palettes. So the sequential palettes are used for data that are ordered. You can think of this as being used for numerical data or continuous data. It doesn't have to be continuous, but the idea is that the data are ordered from low to high. The diverging palettes can be used for data that kind of diverge or they deviate from something. For example, if you have a bunch of data and you want to show the deviations from their mean, then you might want so this way, in this sense, that there's data that can be positive and there's data that can be negative, and they can, as they go away from whatever that center point is, maybe that center point is 0, they can get bigger in 2 different directions, maybe going negative and going positive. So that's a diverging set of data, and you want to use a diverging color palette to represent that. The last color palette is the qualitative palette, which is just used to represent data that are not ordered. So these can be factors or categorical data that don't have any specific ordering, they just have different values. So the palette information that you get from the R Color Brewer package can be passed to functions like color ramp and color ramp palette to be used in the plotting functions in R. So these are the various palettes that are found in the R Color Brewer package. The top set here, these are the sequential palettes, and you can see that they basically go from light to dark as you go from left to right. But they travel through a different set of colors on each palette. So the top one here goes from yellow, orange to red. And then the bottom one here is called the blues palette. It just goes from a light blue to a dark blue. So these are used for ordered data, for numerical data that have a low and a high. The second set of palettes here is the qualitative palettes, and these are used to represent categorical data. And you can see that the colors in the palettes don't really have any specific ordering. They don't go from light to dark. They don't go from any specific order, but they do. So they just have a certain set of colors associated with them, and each palette has basically a theme. Some palettes are kind of bolder than others, and some are more on the pastel side. The last set of colors you can see are the diverging palettes, and the colors in this palette, you can see that they are kind of light in the middle, and as you go from left to right, they get darker in different color ranges. And so you can think of that, the left being negative and the right being positive. And so these are and that's how they diverge. And they travel through different sets of colors here. So the top one here goes from a red, from the left all the way to a kind of purple blue on the right, and then the bottom one here goes from brown on the left to kind of blue or green on the right. So you can choose your palette here depending on what kind of color scheme you prefer. So the Color Brewer package can be loaded into library. After you install it using the install.packages function, you can do library rColorBrewer. And then the brewer.pal function is really the only useful function in the package. And it takes two arguments. The first argument is the number of colors that you want for your palette. And this is usually small. It'll be 2, 3, or 4. You don't need that many blotches on your palette for the primary colors. And then the second argument is the name of the palette. And the name of the palette really is not easy to remember. You just have to look in the help page for brewer.pal, which will list all of the names of the palettes that are available. So here I'm using a blue-green type of palette. And I want 3 different colors from that palette. So now you can see that the character vector that it returns has 3 colors. And they each have a mix of red, green, and blue. And if you're fluent in hexadecimal, you'll know what these values are. But it's not really important to know exactly what the colors are. You'll be able to see them on the screen. So what I'm going to do is I'm going to pass this palette of colors into the ColorAmp palette function. And it's going to return a function that I'm going to call pal. So now I'm going to create the image of this volcano using the image function, but I'm going to, instead of using the heat colors or the topo colors palette, I'm going to use this palette that I've got from the Color Brewer package. And so I'm going to specify that I want 20 different colors to be represented in this image. So the 20 colors are going to come, they're going to be interpolated from this blue-green palette. So the resulting image looks something like this. And you can see that as it gets higher, the colors get darker and more green. And at the lower elevations, the colors are lighter and more blue. Another function that uses the Color Brewer palettes is the smooth scatter function, which comes with R. And this function is particularly useful if you have to plot a lot of points, make a scatter plot of a lot of different points, and you don't want to just have a bunch of dots on the screen that are overlapping each other. So here I'm plotting 10,000 points, and if I were to just plot this on the screen using the plot function, I would get a mess of points that are kind of overlapping each other. It's kind of hard to see the details. So the smooth scatter function, what it does is it creates a histogram, a 2D histogram of the points in your plot, and it just plots the histogram using a certain set of colors. So the default set of colors that it uses is the blues colors, the blues palette in the rColorBrewer package, which is a sequential palette, and it gets kind of darker blue as you get higher and lighter blue as you get lower. So the darker blue areas of this plot are the high density, so that's where most of the points are in the high density region, and the lighter blue parts of the plot are the lower density regions of the plot. So there are a couple other functions that may be of use to you. One is the RGB function, and the RGB function takes arguments for red, green, and blue, and what it returns, so these are numbers between 0 and 1 for red, green, and blue, and it will return a hexadecimal string that can be passed to functions like image or plot. And so if you want to convert between a a kind of decimal red, green, blue representation to this hexadecimal string, you can use the RGB function for that. Another thing that you can use RGB for is to add transparency to your colors. And so there's a fourth argument to RGB, which is a number between 0 and 1, the alpha parameter, which can be used to specify transparency in your colors. 0 being the most transparent, or basically completely transparent, and 1 being not transparent at all. Lastly, I'll just mention the color space package, which can be used to exert a different type of control over colors. You may want to explore it, but I won't talk about it here. So just a quick example of the transparency in R. So here's a plot of about 1,000 points, and you can see that in the high density region here, I'm using the PCH19, which is a solid circle. In the high density region, all of the points just kind of overlap each other. So you just see a black blob there in the middle, and it's kind of hard to see what the resolution is for the different points because there's no definition of points there because they're all overlapping. So if I add a little transparency to the plot, you'll see that the circles become transparent. So when they overlap each other, you can kind of see through them, and so that the areas where there are lots of points overlapping, they get darker, and where there are areas where there are no points overlapping, you just see kind of a transparent circle. So here I've got the code that I've used to create this plot. And you can see that I've specified an alpha parameter of 0.2, and the red, green, and blue are all 0 so I can get black. And so 0.2 is pretty close to 0. There's a lot of transparency. But you can see that when I use the transparency like this, it's kind of a cheap and easy way to get essentially a histogram estimator because the darker areas will represent higher density areas of the plot, and the lighter areas will represent kind of lower density areas. So you can see a little bit more information when you have a plot with a lot of different points in it when you use a little bit of transparency. So that's the basic intro into the use of colors and transparency into R. I think that the careful use of colors in plots and maps and whatever can make it easier for the reader to get the point that you're trying to make, or to see the comparisons that you're trying to make, and I think it's useful to have a good set of colors, especially to match kind of sequential colors with sequential data and diverging colors with diverging data. The R Color Brewer package is a very useful package that's available on CRAN, and it provides these color palettes for the different types of data that you might be plotting. The color ramp and color ramp palette functions are essential when you're trying to interpolate between colors, especially if you're using the R Color Brewer package and you want to interpolate between the colors on a given palette. And then finally, transparency is very useful because it can be used to clarify plots that have many points on them by allowing the colors to be transparent and to kind of overlap each other.